Hi, I'm Blake, and welcome to the Physicist's Guide to Success. I'm sure most of you know what Newton's laws are. They're one of the first things you'll learn in any high school physics class, and are staple lines in pop culture. And this isn't due to any coincidence. Newton's laws are the backbones of the first 2 semesters of calculus-based physics, and define the ideas in classical mechanics. You're going to have to know them because they're vital to you next year. So, without further ado, let's dive into Newton's laws.
The first of Newton's laws is the following. Every body persists in its state of being at rest or of moving uniformly straight forward, except insofar as it is compelled to change its state by force impressed. This essentially boils down to the famous quote, "An object in motion will stay in motion unless a force acts upon it." Think about it. Inanimate objects usually don't move by themselves. For instance, if you have a large box on a flat slope with no friction, air resistance, or air, it won't suddenly move just because of random chance. If nothing is putting a force on the object, it won't move. Going back to our example with the box, imagine if it was pushed and it started moving. Would it keep moving forever, or would it eventually slow down and come to a stop? Well, if this was the real world, then of course something moving like that will come to a stop. Whether it be friction or air resistance that's acting, there are forces that act on the body that will force the box to a stop. Of course, this is physics. We're dealing with the theoretical for now. If there were theoretically no air resistance or friction, the body would continue to go on forever and ever. If you were really deep in space and you push the box out, it will go in the same direction at the same velocity forever, or until it collides with something or enters another body's gravitational field. There's no forces that act on the box, nothing to make it stop. In a similar manner, there's no forces that act on the body to make it move faster. It will continue at the same velocity forever. Another caveat. If an object has no forces acting on it, it will not go in any direction besides the one it is currently traveling in. If it were to change direction, that would technically mean changing its velocity, which means there must be a force. Thus, no forces means same direction. Okay, it's a nice law. It describes something that physically makes sense. However, this is physics. How can we use this in an equation? Well, the way we express it mathematically is the following. The sum of the forces equal to 0, and that means that A is equal to 0. If there are no forces, the objects won't speed up or slow down. But you may be wondering, if you apply a certain amount of force to an object, how fast would it start moving? Well, that's what Newton's second law is for. The second of Newton's laws is the following. The alteration of motion is ever proportional to the motive force impressed, and is made in the direction of the right line in which that force is impressed. This quote relates the change in motion to the force on an object. In this quote, the motion Newton was talking about is not just the velocity, but rather its momentum, which is the velocity multiplied by the mass. The quote essentially states the famous law F equals ma, kinda. Originally, Newton stated the law as the following. F is equal to dp dt, which is equal to dmv dt. We can use this formula to derive 2 essential equations in Physics 6. For now, we'll derive the version that has the acceleration with it. We'll assume this. Mass is constant in a system-body. If we say that, the m in the equation can pop out and becomes constant, so F is equal to m dv dt. As we know that A is equal to dv dt, the equation becomes F equals ma. Of course, this only describes the effect of one force on the body. If you want to look at the acceleration of the entire body due to the forces on it, we say that the sum of the forces is equal to the mass of the body times the acceleration of the body.
Something very important. Like in kinematics and projectile motion, we can split the forces into force components going in perpendicular directions. For instance, we have here the x direction, then the y direction, and even the z direction. So, we could also rotate our coordinate system to fit our problems, like if an object was on an incline. Of course, we must always denote these things. So when you do a problem with forces, remember to always do these things, or else you'll get points marked off. Or you can even get a problem entirely wrong. First things first, draw a free body diagram. So draw an FBD. So this essentially means drawing the object by itself, making it isolated from its environment, including the ground and other objects touching it as well. For instance, let's pretend we have, let's pretend this is down here. We have a little box and we're pushing down on it at an angle. Or let's have it not be, we're not pushing down. How about it's
how about like this? We can have a little rod going at a certain angle that's essentially hitting the box. So first thing to do, we draw FBD. There you go, we have our force, we have it isolated. Second, put in forces. Usually, when an object touches another object, there are one or more forces that the objects exert on each other, which are called contact forces. We're also going to have to draw in non-contact forces, which include gravity, the electric force, the magnetic force, which the last two are known as the Lorentz force, etc. For now, you only need to know about gravity. So usually when objects touch each other, they produce a normal force. A normal force is a force that is perpendicular to the surface of contact. We say it's normal because normal as in like unit normal, how it's normal, it means perpendicular. Normal means perpendicular. It essentially is the resistance of an object that prevents another object from falling into the object. Okay, that's kind of complicated, but this is the way you should like to think of it. I usually like to think about it in terms of video games. Usually in video games, the floor exerts a force up onto you so you don't phase into the ground. However, if you turn on no clip, that's like removing all the normal forces. This allows you to phase into objects and go through walls. So the normal force prevents objects from melding together. So if we look here, there's going to be a normal force that prevents the object from melding into the ground. So there's going to be a normal force going up. We're also going to add in the weight here, which is going to be mg. Lastly, we're going to add in another force. Technically, it's going to end up like this. There you go. With a little angle. We can call this anything we want. We could call it normal too. Let's just call it force, just because we can. Lastly, or not lastly, third step is to label your FBD. So it's always important to label it because if you're having someone look over your work, like your professor when grading your exams, it's very difficult to understand a diagram if you don't know what it's referring to. For this, it's pretty easy to see that it's obviously referring to the box, but when you get to problems with a bunch of boxes, it kind of becomes complicated. So let's draw it in here. FBD of box. 4. Draw a coordinate system. It can be standard or rotated. Just label it so you and your grader are on the same page. This actually becomes very important when you do the 5th step, which is the sum of the forces. So the only way you can say sum of the forces in the y direction or sum of the forces in the x direction is if you know which direction you're talking about. So if we have it like this, then we can say the sum of the forces in the y direction is, as we said, if it was static, it's 0, right? So if it's 0, then we can just isolate the force. It's going to be negative force, sorry, not cosine, why am I saying that? For sine theta plus normal minus mg is equal to 0. So then if we just solve, it's going to be 1 over sine theta times n minus mg. So just remember these 5 steps and you should be good on all of these force body problems or forces problems. The last of Newton's law is Newton's third law. Oh, duh. It essentially states that every force has an equal and opposite reaction. So it essentially says F of AB is equal to negative F of BA. We don't have to use this notation, but it's just important that when you see 2 different force body diagrams on 2 objects that are touching each other, you have to know how the forces are going to be pointing. This is important for normal forces, as the normal force in one free body diagram will be reversed in another, as I just said. However, how can this even be possible? Wouldn't that mean that all forces cancel out? Well, no. Forces can be on different objects, meaning that each force are against each other, but they are not acting on the same body. For instance, let's pretend you're like, ooh, this is really bad. you're punching an object. Yeah, I don't even know what that is. Let's say you're punching an object and you just want to draw a free body diagram. So a free body diagram of fist is going to be equal so there's going to be a force like this, right? But then if we have the free body of box, there's going to be this. So as you can see that they're in the same magnitude, but they're just going in opposite directions. And that's just because of Newton's third law. So that's really all you need to know about Newton's third law. It's this is the only really mathematical thing about it, so it's just a pretty simple law when it comes down to it. So let's do an example problem. Let's pretend we have a box on an incline like this, theta, and then let's pretend that there was no friction on the surface, and then there's another box on top of it. So let's pretend you're asked to find the free body diagram of this right here, the lower box. What do? And solve for the normal force going into the box from the ground. The first thing we have to do is we have to label our first force body diagram. So we're going to call it FBD of lower box, just so we're nice and clear with it. Next, you want to isolate the box from the ground or any contact forces or in contact. So it's going to be theta here. So then we're just going to go and draw the box here. So since it's making 2 points of contact, one from the ground and one from the box above, we're going to have two contact forces here. It's going to be, one is the normal force on the ground, we'll call this N1. Another one, normal force of 2. Lastly, we have to draw in the weight of the box, so the non-contact forces. How many should we draw in here? Well, we should draw in one. One because we're not going to be accounting the box above its weight. That's all factored into N2. For now, we're just going to be looking at this one, M1G. M1 because this is the massive box 1. So then, last thing we have to do is find the coordinate, or place our coordinate system. Usually in problems we like to do it in the standard way just because it's easier for us to understand and it's less trigonometric functions. However, due to this incline, we have 2 of the 3 forces going in some direction of theta, whether it be parallel or perpendicular. So we can actually just put the coordinate system directly on the incline like this. When we do that, we can just do sum of the forces in the y direction to isolate N1. So if we do sum of the forces, this N2 and N1 are actually straight up in the y direction from the coordinate system that we have. So it's going to be N1 minus N2. And lastly, we have to count in the weight. However, we have to multiply it by some trigonometric function. But how do we do that? Theta is definitely not something we know in this coordinate system, so what do? Well, let's just draw out the geometry. So this is the weight here, and this is the normal force 1. If we were to draw out our little box here, right, or our little incline, and this would be theta. Well, what's pretty interesting is that this over here is another right angle. So theta would be, this would be 90 minus theta, so then this must be theta. And so then if we're forced to calculate this distance right here, that's actually just going to be the cosine of theta. And then we just solve for N1. So geometry is going to be very important to your Newton's law stuff, so make sure you have a pretty good understanding of geometry.
So if you wanted to solve for this in terms of knowns, you'd actually take another free body diagram, the upper box, and you'd find that it would be M2 is going to be found in terms of theta, M2, and gravity. Then you can just plug back in and solve for N1 and boom, you have everything you need. So I'll leave that part up to you. It's not as bad as this, but still there. Remember to always include the incline, even though it's not directly beneath it. So that's all for today. This is the Physicist Guide to Success, and thank you for watching.